Picture a neural network humming along, processing text smoothly. Short prompts, clean outputs, no problem. Now watch what happens when we start feeding it more. 10,000 tokens, 50,000, 100,000. See how the nodes start dimming? The connections start fading? By the time we hit 200,000 tokens, the network is barely functioning. Information that went in early is getting pushed out, overwritten, lost in a fog of noise. This is called context rot, and it is one of the biggest unsolved problems in AI today. Information degrades as context grows, and every major language model suffers from it. But in 2025, a team at MIT published something that changes the game entirely. They call it Recursive Language Models. Let's understand why this matters. Every language model has a context window, a fixed amount of text it can process at once. Think of it like a progress bar. As you feed in more tokens, that bar fills up. And here is the critical thing. At first, the model handles it fine. But past about 50,000 tokens, performance starts degrading. By the time you max out a 200,000 token window, accuracy has fallen off a cliff. The model technically accepts 200,000 tokens, but the effective context, the amount of text it can actually reason about accurately, is far less. Think about that gap. That is a massive difference. And it means current models are fundamentally limited when you need them to analyze long documents, large code bases, or extensive research papers. So what has the field tried? 3 main approaches. First, expand the window. Just make it bigger, right? Go from 128K to 1 million to 2 million tokens. The problem is that cost skyrockets and performance still drops. Bigger does not equal better. Second, summarization. Compress the context into a shorter form before feeding it to the model. This works to a degree, but it is lossy compression. Critical details get thrown away, and you cannot get them back. Third, retrieval augmented generation, or RAG. Store documents in a vector database and retrieve relevant chunks on demand. This is great for simple lookup queries, but when you need dense reasoning across multiple sections of a document, RAG returns disconnected snippets rather than integrated understanding. None of these fully solve the problem. Then came a completely different idea. The breakthrough starts with a single insight that changes everything. Instead of treating context as input, something the model has to memorize and hold in its head, treat context as an environment, something external that the model can explore programmatically. Do not memorize the book. Learn to search it. This is the core idea behind recursive language models. The architecture has 3 components. First, the root model. This is your main language model, the orchestrator. It does not try to read the entire context. Instead, it plans a strategy and writes Python code to explore the data. Second, the Python REPL, which acts as external memory. The full context, whether it is 450,000 tokens or 10 million, lives here as a variable. It never enters the model directly. Third, sub-LLMs. These are smaller model instances that receive only targeted snippets, maybe 3,000 tokens each, and process them before returning results. The root model writes code, dispatches tasks to sub-LLMs through the REPL, collects results, and synthesizes them. The context never overloads any single model. Each component sees only what it needs to see. Let's walk through a concrete example. Imagine you have a 1,000-page legal document, 450,000 tokens. A traditional LLM simply cannot handle this. Here is how an RLM tackles it step by step. Step 1. The entire document gets loaded into the REPL environment as an external variable. The model never tries to ingest it directly. Step 2. The root model writes Python code to split the document into sections and search for relevant content. It splits the document into 150 sections, then filters for the keyword liability, narrowing down to 23 relevant sections out of 150. That is programmatic exploration, not brute force memorization. Step 3. Those 23 sections get dispatched to sub-LLMs. Each sub-LLM receives only about 3,000 tokens, a completely manageable amount. They analyze their section independently, and the results flow back. Step 4. The root model collects all results and synthesizes them into a comprehensive liability analysis. The beauty here is that the system handled 450,000 tokens without any single model seeing more than a few thousand at a time. No information loss, no context rot, no degradation. But why do we need the sub-LLMs at all? The Oolong pairs benchmark illustrates this perfectly. The task is to classify 5,000 data entries and find patterns between them. With just the REPL and no recursion, the root model uses keyword heuristics, simple if statements looking for categories. It scores 43.93 on the F1 metric. Not bad, but ambiguous entries trip it up. With the full RLM approach using recursion, the root model identifies ambiguous entries and asks sub-LLMs to classify them using actual semantic understanding. The score jumps to 58.0. And for reference, the base model without any RLM infrastructure scores essentially 0.04 because it simply cannot process that much data. The lesson is clear. Use code for structure and deterministic operations. Use LLMs for semantic understanding. That combination is what makes recursion so powerful. The scale improvement is dramatic. Traditional LLMs handle about 128K tokens, roughly one book. RLMs handle 10 million tokens or more, an entire library of over 100 books. That is roughly 100 times improvement. This unlocks real-world applications that were previously impossible. The benchmarks back this up. On BrowseComp Plus, which requires processing 6 to 11 million tokens of context, RLMs achieve 91.33% accuracy. The base model scores 0 because it literally cannot run on that much data. To be fair about limitations, RLMs introduce higher latency and require models that are good at code generation. They are not always faster than a direct query on short contexts. But for long context tasks, there's nothing else that comes close. Here's where it gets even more exciting. What if you train a model specifically to be recursive? The researchers took Qwen3 8b, an 8 billion parameter model, and created RLM Qwen3 8b. Same size, same architecture, but trained differently. A large teacher model, Qwen3 Coder 480b, generates example trajectories showing how to decompose complex tasks recursively. These trajectories get filtered for quality, and the smaller model learns from them. The result? A 28.3% improvement over the base model. The trained model learns when to recurse, how to decompose problems, and what to inspect. This is the first natively trained recursive language model, and it approaches much larger models in capability on certain tasks. Let's put RLMs in context against the alternatives. In a head-to-head comparison across 4 criteria, expanded context windows only partially handle long context, struggle with dense reasoning, but avoid information loss at the cost of retraining. Summarization handles length, but struggles with reasoning and introduces high information loss. RAG handles length, has limited reasoning ability, avoids info loss, and needs no retraining. RLMs excel across the board. Excellent long context handling, excellent dense reasoning, no information loss, and no retraining needed. But here is an important nuance. RLMs are complementary to these approaches, not a replacement. An RLM can use RAG as one of its tools. It can use summarization within its pipeline. The power is in the orchestration. Where is this heading? 3 frontiers are opening up. First, deeper recursion. Current RLMs mostly use depth 1 recursion, but the framework supports depth 2 and beyond, where sub-LLMs can spawn their own sub-LLMs. Second, multimodal extension. Imagine an RLM that can explore not just text but images, video, and audio as external context. Third, learn decomposition policies, where the model learns optimal strategies for breaking down different types of problems. Zoom out, and you see RLMs representing an entirely new axis of AI scaling. We have had traditional scaling with larger models. We have had reasoning scaling with test-time compute. RLMs add a third dimension, inference structure. This is not about bigger models or harder thinking. It is about smarter memory management, teaching AI to use external memory the same way we do. We do not memorize encyclopedias. We learn to navigate them. To recap, context rot is real and limiting current LLMs. Recursive language models treat context as an environment, not input. They have proven 100 times scale improvements, going from 128K to over 10 million tokens. And they work as a drop-in replacement for standard LLM calls. The code is available on GitHub, the paper is on arXiv, and a pre-trained model is on Hugging Face. Links are in the description. If you found this useful, subscribe for more deep dives into the latest AI research. Thanks for watching.